So in this video we'll be going over the first theorem in number theory, which is called the basis representation theorem, and a lot of you will understand it after we talk about what it really means. But for now, let's give the formal definition of the theorem. So we're going to first define some variables. So let k is going to be any positive integer greater than 1. And this is the same definition we used for k in our theorems in the last video. And then we're going to let n be any positive integer. Then we're going to say that there exists a representation that looks like this. So I'm going to write this in different color just for emphasis. We're going to have n equals a naught. Let's do a naught. Why not? Okay, a naught k k to the s plus a1 k to the s minus 1 plus dot 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 plus a sub s, where a naught does not equal 0. Each ai is non-negative, so it can be 0, it just can't be a negative number, and each ai is less than k. So we're going to say that this representation, the theorem says that this representation is unique and is defined as, and is called the representation of n to the base k. Okay, so in this video I think we'll just go over what the theorem really means. In the next video we'll go about proving it. So basically, I think everyone knows this theorem. What it means is, if we take some, k is our base, so we're gonna, we usually work in base 10 when we're doing all our calculations. So in our case, k equals 10. And n is the number we're trying to represent in base 10. So let's pick some arbitrary n. Let's just pick like 216. So 216 is our n. So we're going to try to write it in this notation, 216. So we're going to go about and do it how we did in elementary school or earlier. We're going to say how many. So first we're going to say, what is the largest exponent that we can raise k to so that it's not greater. So if we raise k to 3, 10 to the 3 is 1000, which is too big. But if we raise k to 2, this is 100. And how many hundreds are in here? 2. And then, so now there's 16 left over. So our next one is going to be 10 to the 1. And we're going to have 1, 10. And then we have unit digits, or units place. And there's 6 times 10 to the 0. We all know how to do this. This is pretty common. And many of us also know how to do base 2. So we'll just go over that really fast. Let's do it in like, we'll just use some little corner from the last video. Base 2. So let's say base 2. So we're going to have k equals 2. And let's try to represent n equals, let's say, 18. So 2 to the what exceeds 18. So if we do 2 to the, let's say, 4, that's 16. So that's okay. 2 to the 5 is 32. So that's not going to work. So we have to say 2 to the, what was it, 4, right? Yeah. 2 to the 4. So how many 16s are in here? Just 1. So we're going to have 1 times 2 to the 4, 16. So how much is left over? Is 2. So we're going to go ahead and write the other terms. So 2 to the 3 plus 2 to the 2 plus 2 to the 1 plus 2 to the 0. But in reality, there's only 2 left over. So we know the coefficient of 2 to the 1 must be 1, and all these other ones must be 0. Which, remember, is okay because they just can't be non-negative. So if we simplify this, this looks like 1 times 2 to the 4 plus 1 times 2 to the 1. And that's our, if we use the notation of what the theorem says, that is our representation of 18 to the base 2. And the theorem, what we're going to try to prove, is that this representation is unique, which means that, for example, in this one, there's no other possible way we could have written this in our base